So, so I'm going to try to pick up where we were in our class last Monday. And so we talked about, linear systems of equations and what can happen when you try to solve those. And we figured out that there were three possibilities. One is that there's no solution. One is that there is exactly one solution. And another way to say that is we say it's a unique solution. And the other possibility is there's an infinite number of solutions, right? So I'm going to kind of revisit, not the exact problems, because I can't remember what we looked at last time, but I'm going to revisit that just a little bit. And then I'm going to try to put it in the context of how you would attack solving a system of equations when you have multiple or many or let's just say several variables and several equations. So I talked last time about how when you only have two equations and two variables, it's easy to solve. But even when you've got three variables and three equations, then it starts getting a little more difficult. And if you want more than that, it's you really need an algorithmic approach. Something that's going to work every time. Instead of kind of a hook or crook, let's see what the numbers are and see what I can make work kind of approach. So that's what we're going to do today. We're going to talk about, a more algorithmic approach to how to reduce a system of equations so that we can get a solution easily. So there's a couple of things that we need in order to do that. So one relates to converting a system of equations to a matrix. So we talked about that last time, but let's just redo that. So let me kind of reorganize here just a sec. All right, so let's just look at let's start with this system. So it's going to be 6x 2y equals 4, 3x plus 4y equals 10. All right, so to put that in a matrix, we just create a matrix, and it looks like this. So we have a column for each variable. So x is a variable, and the coefficients of x are 6 and -3. We have a column for y, and its column looks like that. And then we could just stop at that. And we typically, we call this the coefficient matrix because it's a matrix of coefficients. And we typically call it A. That's just kind of convention. There's nothing magic about that. It's like you call your variable X or Y or Z or W or whatever. But typically we refer to the coefficient matrix as the matrix A. And then we have the right-hand side, which in this case is 410. So this is the right-hand side, and so we kind of distinguish between the terms matrix and vector. So a matrix is a two-dimensional kind of table, whereas a vector is just a column, or it could be a row. But we'll this is the language that we'll use throughout the semester. Now, when we're solving a system of equations, especially early on, we will,
What?
okay, Carlos, oh, there you go. All right, so when we're solving a system of equations, especially early on in the semester, we will mostly deal with what we call the augmented matrix. And so in our case, that looks like this. All right, and sometimes, especially early on, I'll draw a line there because it makes a distinction between the coefficient part of the matrix and the right-hand side part of the matrix. But later on, you shouldn't get comfortable with that notation because in your book, it will, and I in class will not always put that line there. But you'll be told this is an augmented matrix or this is a coefficient matrix. And which one of those it is will matter. But for now, we'll just, we'll keep it simple. We'll just start off with this augmented matrix, and that's what we're going to deal with. So, basically all we've done is just kind of did a shorthand version of that system of equations. So if we were going to solve this system and we don't know anything about matrices, then one thing we might do, there are a number of ways you could approach this problem, but one thing we might do, so I'm doing a little bit of an aside now, so let's kind of forget about the matrices stuff or matrix stuff for just a minute. But one thing I might do is, I'm looking up here and I see we got, I got a 6 and I got a -3. And so in my mind, I'm thinking, oh, okay, so, 2 times -3 gives me -6. And so if I do -6 plus 6, then the x's will go away. And so, let's talk just a little bit about how that looked. Okay, so what I'm, all right, I'm going to move down here. So I'm going to say, I'm going to multiply the first row or the first equation by, let's say, by a half. Okay, so I'm going to do a half times the first equation. And I get what? I get 3x minus y equals 2. And then I'm going to leave the second equation alone. And it's -3x plus 4y equals 10. And then I add those together, right? And the x's go away. And what do I got? I got 3y equals 12. So y equals 4. And then I could plug back in and figure out what x is, right? So that's kind of one way to approach this. So we're actually going to do that exact same thing on the matrix. So to preface this, so today I'm going to be hitting topics in section 1.1 and 1.2 because they really go together. If you have your book, you can look at the beginning, first page of section 1.2, and it has a definition there. And so in that definition, it defines like actually, you know what? That's not what I want to do. Let me see where, oh, sorry. Scratch that last just a little bit. Let's go back to section 1.1. And there's a section called elementary row operations. All right, and it lists 3 of these. And these are like the the things that we can do to a matrix. And it turns out that these are things that we can do to a matrix, in particular to an augmented matrix, without changing the solution to that system of equations. So basically, elementary row operations are ways to do the things that you would if you were just solving the system like you learned how in algebra, but kind of formalized. And the important thing is that when you do any of these elementary row operations, you're not changing the solution to the system. All right, so these are actually the operations we're going to do so that we can simplify the system and easily figure out what the solution is. So one of these operations is called replacement. And it means to replace a row by the sum of itself and a multiple of another row. All right. So if you look up here at what we just did in here, that's exactly what we did. Maybe not obviously, but what we did was essentially I took the second equation, all right, which is right here, and I replaced it by the sum of itself. So here's it, and a multiple of another row. So here's my multiple of another row. And so here's where we added those together, and this is what we ended up with. So essentially at this point, my system looks like whatever it originally was, 6x minus 2y equals 4, and y equals 4. All right, so kind of this step of multiplying the first equation by half, think of that as doing it in your head. Think of it as we didn't actually change the first row. We just kind of multiplied it by a half in our head and added to the second row. The second row got replaced by the result of that, which is y equals 4. And so now our system looks like this. First row is still the same. Our first equation is still the same. Second one is now this. And now that we have that, right, we can substitute back in and figure out what x is. So in terms of our matrix, right? So if we did that with our matrix, and I'll show you how I write that. So I write that as we're doing 1/2 row 1 plus row 2. So this means replace row 2 by 1/2 row 1 plus row 2. All right. And so that means row 1's not changing. So it's still 6, -2, 4. And row 2, so we do this this computation just on the matrix. So I'm doing 1/2 row 1. So I'm doing 1/2 times 6. So I'll write this out. 1/2 times 6 minus 3. And here's going to be 1/2 times -2 plus 4. And same thing here, 1/2 times, excuse me. 1/2 times 4 plus 10. All right, which is just the same arithmetic we did earlier. So this is still 6, -2, 4. And now this is here, we got 3 minus 3. So that's 0. Here we've got what? 1/2 times -2 is -1 plus 4 is 3. And 1/2 times 4 is 2 plus 10 is 12. All right. And then clearly this row right here corresponds exactly to that. So I guess actually probably over here I should have written 3y equals 12 instead of y equals 4. I did a little little extra step there. But notice that once I get to this point, right, then, you know, it's same as this. And so let's assume we don't know about this stuff here, right? Then I'm going to say, okay, I've eliminated the x, and so I can go from here and say, okay, so 3 times y equals 12, so y equals 4. I've solved for y, and then I can substitute back into the first row, right? 6x minus 2 times 4 equals 4. So 6x equals, let's say, minus 8. So plus 8 is 12. So x equals 2. And, you know, so I end up, here's a solution to my system. Now, you're probably sitting there going, oh my God, isn't this like so much work? Because, you know, it's easier just to do it the way, you know, I was doing it down here, right? We already know how to do that. That's easy. And I would agree with you. So remember, I prefaced all this with, we want a way to an algorithmic way to approach a system that has, you know, several variables, several equations, and have a way that, you know, it's going to work no matter what our numbers are, and so forth. So that's what we're doing here. So any questions at this point? All right, so let's see. Let me just quickly here finish out. I said there were 3 elementary row operations. This one that we just talked about, replacement, is by far the one you're going to use the most. But for completeness, I'll say the other 2. One is swap rows. Swap 2 rows. All right, so you know, as we know, that's just like reversing the order of the equations, which has no effect on the solution of the system. And the reason why we include that as one of the elementary row operations is because we're going to, our goal is going to be to get the matrix in a particular form, which is what I started talking about earlier and then said, oops, I need to back up. So it's called echelon form or reduced echelon form. And so one of the parts of it is that if there's any rows that are all zeros, we want to put those at the bottom. And so to do that, sometimes you have to swap rows. The other elementary row operation is to multiply a row by a scalar. So this actually changes the row. As opposed to in the replacement operation. Okay, so that just means that, you know, I see a row, and this is also mainly just to get it into one of these forms that we're talking about. Sometimes we want a particular entry in a row to be a 1. And so to get a number to be a 1, we need to be able to multiply by the reciprocal of that number. So as I said, operations 2 and 3, not that big a deal. 1 is the one you're going to be using all the time. Okay, so at this point, we need to let's do this. It turns out that let's see. It turns out that this system here, well, we know now. Oops. Yikes. You guys still see my iPad?
Yeah, we can see that same note now.
Okay. Did it go away and come back?
It went black, yeah.
Okay. Okay. I don't know what happened there, but all right. Okay. So, let's see. So we just showed for this system that it has a unique solution, right? We solved the system. It has one solution: x equals 2, y equals 4. So the way that this matrix looks is important. So really, we're interested. Well, I guess I was going to say we're really interested in just the coefficient part, but that's not entirely true. So, excuse me. All right. So, so remember this, right? We needed to get a value for x and for y. So remember, this is the x column. This is the y column. And so to get a value for y, we had this non-zero value here, right? So this row down here amounted to 3y equals 12, and we could solve for y. And then we could do something called back substitute. So basically substitute that in for y up in the first equation and solve for x. All right, so what I want you to think about is, so here, right, so this one has a unique solution. How would we know if we had a system that, was one of the other cases, had no solution or had an infinite number of solutions? So let's just let's play a little bit. So let me go down. Let's start over here. How about if I had this is a similar system: 6x minus 2y equals 4, negative 3x plus y equals 5. Okay, so it turns out this system has no solution, and if you look closely, you can see that. But let's assume that we're not noticing that, and so this is how we would proceed, right? So think about, okay, here's a problem in my homework. I'm supposed to solve this system. So what would I do? Well, first I'm going to put it in augmented matrix form. Oops. Not why. One of my friends asked me this morning if I was having brain fog, since that seems to be a common symptom of COVID. And I told her I didn't think so, but I don't know. We'll see, because this is the first time I've really had to think. So we can decide after this if I have brain fog. If I make mistakes, I'm going to blame it on that, okay?
I respect it.
Thank you. All right. Okay. So, so basically, I'm going to kind of talk in terms of this algorithm that I have been referring to. So actually, the way we start is, if possible, we want to get a non-zero value up in this upper left corner. All right. And if we have that, if we don't have that, then we would try to swap rows to create that. But in this case, we don't need to worry about that. We already have a non-zero value here. And so what we want to do is zero out underneath it. So basically, we want to just make this first row the only one that has an X in it. All right. So we're going to zero out underneath, which means I want to make this a 0. And so I just have to figure out, what row operation do I need to do to make that happen? So I'm not going to change the first row. And so basically I need to do the same thing as I did before, because the system really, this part of the system hasn't changed. So I need, let me write this down. I want to zero out this position. So I'm going to do a half times 6 minus 3, right? Gets me a 0. So I'm doing that same operation. I'm doing a half times row 1 plus row 2. All right, so replace row 2 by 1/2 row 1 plus row 2. All right, so we know that's going to be a 0 there. This next one.
I have a
oh, go ahead.
Why can't we just multiply the row by 2?
The second row.
Yeah.
You could. And as I said, that there's two different things going on here. One is, do I want to solve the system by whatever way I can? In which case, I would agree with you. I would multiply the second one by 2 and add them together and go with that. But that's not really what I want to get across to you. What I'm trying to get across to you is what's a systematic way or an algorithmic way, which doesn't involve you really looking at the numbers and going, oh, look, there's a 6 and a -3, so I can multiply by 2 and get rid of that. I want something that's going to work no matter what the numbers are. Like an approach that's going to work no matter what the numbers are. That makes sense?
Yeah.
Okay. All right. Okay, so let's keep going here. So I'm doing a half times row 1, right? So means a half times -2, which is -1 plus 1 gives me 0. So that's a half times -2 plus 1 gives me 0. And then here, so I got a half times 4, which is 2 plus 5 gives me 7. All right, so that's a half times 4 plus 5. All right, so so if I wrote out that second, all right, look at that second row there. If I wrote the equation that corresponds to that, it looks like 0 times x plus 0 times y equals 7. All right, and so that's like, alarm bells should go off. And you're like, oh, well, I can't solve that, right? There's no x and y that satisfy that. And so that tells you there's no solution to this system. Okay, that makes sense. So this is one of those, that's why up here I was saying notice that we've got a non-zero variable here, right? A non-zero coefficient of y, which means that I can solve this for y. But down here, right, nothing going on here, right? There's no solution. So that means the whole system has no solution. Questions here? Okay. All right, I'm going to change this up just a little bit. So I'm going to basically just take that same system, but just tweak it just a little bit. 3x plus y equals -2. All right, so so this one is, if you look at it, those equations are multiples of each other. And so I should end up here with something that tells me that there's an infinite number of solutions. All right. So I'm going to approach it exactly the same as I did that one above. All right. So I'm going to throw it in a matrix: 6, -3, -2, 1, 4, -2. And again, I look and I say, do I have a non-zero value up in the upper left? Yes, I do. Okay, I want to zero out underneath. All right, same steps we went through before. So I'm going to do the same operation: 1/2 times row 1 plus row 2. All right, because I want to zero out here. Zero out this position. All right, and so I'm going to still, all right, my top row didn't change. I didn't change anything there. And the bottom row actually is not going to change until I get to the end, because those numbers are still the same, right? Because I got 3 -1 here, 3 -1 there. So when I do that operation, I'm going to still end up with 0, 0 there. But over here, let's look. So remember, I'm doing a half times row 1 plus row 2. So I'm doing a half times 4, which is 2, plus negative 2. Which gives me 0. All right, that's a half times 4 plus negative 2. All right, so, excuse me. All right, so at this point, now if I look at my last row down here, it just says 0x plus 0y equals 0. Well, big deal, all right? That really tells us nothing. It tells us absolutely nothing because any x and y satisfy that equation. So we're left with, just the first one, which says 6x minus 2y equals 4. This is a line. So infinite number of solutions, right? Anything on that line is a solution. So the reason why I've worked these out like this is because I want you to compare what these matrices look like, in particular, what the second row looks like in these matrices. So for no solution, we end up, right, for no solution, we end up with a row of zeros, but then a non-zero in the right-hand column. Right, that's what gives us this kind of equation, right? That 0 times all our variables added together equals something not 0. And so if we have a row of all zeros in the coefficient part of the matrix, but then something not 0 on the right, that's how we know there's no solution. I'll write that down. All right, so no solution. This happens when a row of the augmented matrix is of the form. All right, so we got 0, 0, however many variables we have, they're all zeros. And then in the augmented column, we have something not 0. So these are all zeros in the coefficient part of the matrix and not 0 in the augmented column.
I have a question.
Mm-hmm.
So looking at the two previous examples, like the first one, since like 0x plus 0y equals 7, there's no solution to that. But with the second one, if the top equation instead of 6, -2, and 4 was like 0, -2, and 4, would it still have infinitely many solutions just because the second one has all zeros?
Yes, it would. Yes. Yes.
Okay, so you only look at the second one that you adapted?
Well, in this case, we've only got 2, so the answer is yes. But even if it was, the main point here is, I mean, you look, basically, you really want to look at all the rows and see if any of them are this form, right? So and by this form, I mean, well, up here really, by this form, I mean, everything over here is zeros and you got something not 0 there. So even if up here you had, if this was a 0, so if you had 0, just assume that was a 0, then it's still fine because you don't have all zeros here. Right? If you end up with all, if these were both 0 and you had a 4 there, then it would be no solution.
Okay.
That's a very good question because, and this is toward the end of section 1.1, there's a, let me back up here. So this is section 1.1. There's your book calls it 2 fundamental questions about a linear system. All right, and number 1 is basically, does the system have at least one solution? Or another way of saying that, and this is a new term for you, is the system consistent? All right, and consistent, consistent here just means there's at least one solution, right? Those mean the same thing, but consistent is a new term. A system means consistent means does the system have at least one solution? Okay, so that's the question that you ask first. So there's 2 fundamental questions, and the order that you ask them matters. So if you excuse me. So if you had, if you had something like just what I was saying, if you had something like this, then that looks like, oh, there's an infinite number of solutions. Actually, that doesn't tell you there's an infinite number of solutions. But the fact, let me go back up here. The fact that we had one row that looked like this and another row that looked like this, where that equation defined a line, that's what meant we had an infinite number of solutions. All right, so it's not just the fact that we have all these zeros that means we have an infinite number of solutions. In fact, this row of zeros means nothing, actually. All right, really doesn't tell us anything. Because as I said, any x and y satisfy that equation, 0x plus 0y equals 0. So it's really what's happening up above. So if up above it looked like that, then this would say no solution, right? Even though we've got 0, 0, 0 at the bottom, because the top says, top says 0x plus 0y equals 4. There's no solution to that. Okay. So question number 1, does the system have at least one solution? And the system, so the answer to this, let me write this. The answer to this is yes, if there is no row of the form 0, 0, not 0. All right. So that's how you answer that question. Now, if the answer to that question is yes, does the system have at least one solution? Then you go to question 2.
I have a question.
Yeah. Oops. Yeah, go ahead.
So it says, I'm just having trouble reading. The answer is yes.
Oh, if, sorry. Yeah, if there is, it's the brain fog. If there's no row of this form.
Thank you.
Yeah, sure. All right, so if the system is not consistent, stop. All right, done. No need to go to step 2, right? Because you've already got your answer. There's no solution. How many solutions, or what are the solutions? There are none. All right, so otherwise, go to question 2. All right, And question 2 is, come down here. Question 2 is there only one solution or an infinite number? Okay, and so to answer that question, you also look at the matrix. All right, so if we go back up here, so if we were looking at this system here, oops, we're looking at this system here, we would get to this point and say, oh, there's a row of the form, whoops, let me get a different color. We'd say there's a row of the form 0, 0, not 0. That implies no solution or inconsistent. Okay, so we're done with that system. No need to look at it anymore. If we were working on this problem, then we get here, and now let me preface this by saying that we need to define, like, for example, I can't, let's see, right? I can't just write down the system and say, oh, look, there's no rows that look like this, so it must be consistent, right? I mean, I can't do that. So we need to talk about what this form of our matrix needs to be, and we'll talk about that in just a minute. But this one's in that form, so trust me for right now. And we get to this point and we say, oh, right, there's no row that looks like this, and so therefore the system's consistent. And then we want to know, okay, it's consistent. We go to question 2, how many solutions are there? Is it just one, or is there an infinite number? And in this case, there's an infinite number, because really all we have left is this first row, first equation, which defines a line, and there's an infinite number of points on that line. Hence, there's an infinite number of solutions. The fact that this position here is a 0, though, is important. And we'll see more about that in just a little bit. Let's see. Okay, we'll get on time so far. Let me go back up to this one, though. So if we get to this point, now this matrix is also in the form that we want to get it in, which again, I'll talk about in just a minute. And what we see here is that I've got my non-zero value here. And then if I go here, I've also got a non-zero value. And it's this 3 here that lets me solve for y, right? That gives me a specific value for y. And since there's a specific value for y that solves the system, there's also a specific value for x, because if I know y, that defines what x is by this equation here. So what's important are looking at the columns corresponding to the variables and seeing if we have these non-zero values. And actually these are in a little later on, we're gonna start calling these pivot positions or leading entries, right? So it's like the 6 is the first non-zero entry in this row, whereas the 3 first non-zero entry in this row. And so we're going to ask questions like, does each variable have a pivot position in its column? Or does each variable have a non-zero value that's a leading entry in its column? All right, so questions here? All right, so that's essentially section 1.1. I'm going to move on to section 1.2. Okay, so if you have your book handy, then the beginning of section 1.2, there's, oops. So this is section 1.2. So there's definition of echelon form and reduced echelon form. Okay, so these have to do with the form we want to get the augmented matrix into when we're solving the system. So just keep life easy. I'm gonna write these down quickly. So for echelon form, one is all rows of all zeros are below any other rows. All right, so if you got a row that turns out to be all zeros, you move it down to the bottom of the matrix. Each leading entry of a row is in a column to the right of the leading entry of the row above it. Okay, so this is what I refer to as the staircase structure. All right, and 3, all entries in a column are a column below a leading entry are zeros. All right, so this is the zero out under a leading entry idea. All right, so I'm gonna this is what I've written here corresponds to echelon form. There's a couple more rules for reduced echelon form. I'm not gonna talk about those right at this moment, because the echelon form is typically all we need to worry about. So I'm going to focus on it right now. So let me all right, so I just want to demonstrate some of this. So I'm going back, I'm looking in my book at section 1.1. Let's see. Well, this looks like a kind of a might be turned into a long problem, but it'll work for us. So this is section 1.1, problem number 12, and then the instructions say just solve the system. So I'm going to write it down in augmented matrix form, just to save some time here, and we'll walk through like the steps to put this matrix in echelon form and to solve the system. Okay, so let me make sure I copied it down right. 3, -4, -3, -7, 6, 4, 7, 2, -4, okay. All right, so so the algorithm, which your book talks about in section 1.2, they call it the row reduction algorithm. So the basic idea, as I said earlier, you start up here at the upper left corner. You want to make sure that's a non-zero value if possible. And again, here it's already non-zero, but as I said earlier, if it's not, then you can swap rows to get a non-zero value there, possibly, unless your whole first column is zeros. All right, so we're restricting what we're doing here to elementary row operations, right? We talked about earlier. And we want to get the matrix in echelon form. So we want it to satisfy these three rules here. So we start off by with our upper left entry. It's not zero. So then we want to zero out below the 1 by using the replacement operation. All right, so we're going to do a couple of row operations here. I'll do them separately just so it's clear for you. But our first one, we want to make this 3 here a 0. So what row operation do I need to do to make this 3 a 0? So what I want to do, I want to use this 1, right? The whole point of having a non-zero value here, so I can use that value to multiply by something, add here, so that becomes a 0. Anybody want to venture what row operation I need to do here?
-3 times
Please.
row 1 plus row 2.
Yes, exactly. -3 times row 1 plus row 2. Right? Because -3 times 1 is -3 plus 3 is 0. So that's how you figure it out. All right. So row 1 doesn't change. So it's 1, -3, 4, -4. And row 3 doesn't change. So I'm just going to write those down because then I don't have to think about them anymore. And I also know that's going to be a 0 because that's how we figured out what we wanted to do. And so now I just need to do the row operation on the rest of row 2. So remember, I'm doing -3 times row 1 plus row 2, and that's the value that goes into row 2. So -3 times -3 is 9, plus -7 is -2. And here, -3 times 4 is -12, plus 7 is -5. And then what? -3.
I have a question.
Yeah.
Wouldn't the middle spot where we have -2, wouldn't that be a +2?
Well, maybe. Let's see. I'll write down what I did. I could be. It's the brain fog, right? I could be wrong. I like that, man. I'm gonna have to keep that going all semester. Let's see. All right, so it would be, so here that would be -3 times -3 plus -7. So that's, oh, you're right. 9 minus 7 is 2. Very good. Thank you. Now, see, if we were in class, I would tell you get an A for the day, and you would get bonus points on the either the previous or the next quiz. So so keep it up. All right, so let's see. Let me just write down these other ones just for clarity for you and to make sure I'm doing it right. So for this -5 here, right? It's going to be -3 times 4. Plus 7, so -12 plus 7 is -5, okay. And then this last one is going to be -3 times -4 plus -8. What is that? So that's 12 minus 8 is 4. So I got a 4 there. Does that look right? All right. So what we have accomplished here is we've gotten a 0 in this position, and we still need to get a 0 here. And we're basically going to do the same sort of thing. We're going to use this 1, multiply it by, we need to multiply it by 4, such that when we add it to -4, we're going to get a 0. All right. So I'm going to just write that like this. So 4 times row 1 plus row 3 this time. All right. And so this time, again, row 1 doesn't change. And this time row 2 doesn't change. And now row 3, it's going to be what? So I'll write these down again. 4, well, I already figured out that's going to be a 0, right? 4 times -3 plus 6. What's that? -12 plus 6, -6 there. Then 4 times 4 plus 2. So that's 16 plus 2, 18. If you see me making a mistake, jump in here. 4 times -4 plus 4. -16 plus 4 is -12 there. All right, any questions here? Okay, we on time. Okay. All right, so let's keep going. So we've accomplished zeroing out underneath that leading entry there. So I guess I should go back up here. It uses this term leading entry. So I'm gonna go back up here and say a leading entry is the first non-zero entry in a row. All right, so we've got, all right, so here's a leading entry in row 1, and we have zeroed out under it. All right, and so now we move over, because we're done with this column, we move over and down, and now we're interested in this 2 here. This 2 now is a leading entry. All right, so it's a leading entry. It's the first non-zero entry in row 2. And so we're going to use it to zero out underneath it. So we want to zero out here, so that we'd have a leading entry here, zero out underneath, leading entry here, zero out underneath. And so that's what we want to do. So we want to make this, we want to zero out right here. And so write that. Zero out this position. All right, so what row operation do we need to do for that?
Times 3, row 2 plus row 3.
3 times row 2 plus row 3. Is that going to do it? That would give me 3 times 2 is 6, minus or plus a -6 is 0. Yes, so that is what we need. So row 1 is not changing. And row 2 is not changing. And row 3 is going to be, we have 0, 0, and then we've got 3 times row 2, so 3 times -5 plus 18. So that's -15 plus 18 gives me -3 there. And then in our last position, we've got what? 3 times -4 minus 12. So I got -12 minus 12, -24. That look right? Okay, so
I got a +3, and then I got a 0 for that augmented.
wow, let's see.
Wouldn't it be a or not a -4?
So let's see, I'm going, yeah, so for this one, I got, so multiplying through, oh, yeah. I was looking at row one. So let's see, is this one right? 3 times -5, plus row 3. So 3 times -5 is -15 plus 18 is a wow. I think it really is brain fog. I'm like way off right here. And I even wrote it down. Right? It's obvious. And I'm still messing up. Okay, earlier I thought the brain fog was a joke. Now I'm like, I'm thinking I need to take it seriously. Okay, so this one over here, what do we got? We got 3 times -4 is -12. Minus 12.
It's 3
Oh,
times
it's row 2. It's row
positive 4.
2. Row 2. Okay, I keep trying to do row 1. Thank you. All right. I'm gonna let one of you guys teach next time. Well, let's take care. Can you teach on Wednesday? And all right. So it's not -4. It's 3 times 4 plus -12, which is 0. All right. Thank you. Okay. So everybody happy with those numbers? We all good with that? All right,
Yep.
So at this point, our matrix is in echelon form. All right, so this is echelon form. If you go back and look at the rules, I'm not going to scroll up because I want to be able to look at this. But the first one was all rows of zeros are at the bottom. Well, we don't have any of those, so we don't have to worry about that. Second one says leading entry in a row. A leading entry of a row is in a column to the right of the leading entry in the row above it. So that sounds complicated, but what it actually is referring to is kind of this, as I said, it's kind of the staircase structure, right? So we have the leading entry in the second row is to the right of the leading entry in the previous row and so forth. So every time it's like you start at the upper left and then you move over and down and over and down. Now, sometimes it can be possible that there are columns that don't have a leading entry, but for now we won't worry about that. You're not always going to have one here, move over down. There's another one, move over down. There's another one. It's not always going to be like that. It might be you have to move 2 over and go down to get to 1. But for now, we won't worry about that. Number 3 is all entries in a column below a leading entry are 0. All right, so here's a leading entry, we got zeros below it. Here's a leading entry, zeros below it. Here's a leading entry, there's nothing below it, so we don't have to worry about it. Okay, so this matrix is in echelon form, which means that we can apply those 2 questions to determine how many solutions the system has. So the first question was, is the system consistent, right? And the answer to that, let's go back. Okay, so this is what's important here. System's consistent if there's no row of this form, right? So this form where you got all zeros and then at the augmented column something not 0, that's what tells you there's no solution. So we're looking to see, are there any rows that look like this? And the answer is what? Yes or no?
No.
The answer is no. The answer is no, because it's asking, do you have a row that looks like 0, 0, 0, and then something not 0 over here? And we don't have that, right? Every row, we don't have any rows in the coefficient part that are just zeros. So question number one, is the system consistent? The answer is yes. There is no row of the form 0, 0, not 0. Okay, so then we go to question 2, which is one solution or an infinite number of solutions.
Would it
Okay.
be infinite?
Why do you think that?
Well, because if it's the 3z equals the 0, then that's just going to be one straight line going from one end to the other.
Well, yes, but that's not the only equation we have, right? We got to use that along with the other two. Right?
I
So
gotcha.
what?
Like, oh, okay, I gotcha.
Yeah. But you're right. If we just had that, then it would be, well, actually 3z equals 0 would be a whole plane, because x and y could be anything, right? It's line with, that's basically the xy plane. But if you remember, we're almost out of time here, so I'll make this short. But remember what happened up here. Right up here, we had in this case we had a unique solution in this case, and I told you to look at each of the columns corresponding to the variables, and do you have a leading entry? And when you do, you'll have a unique solution. It's like down here in this one we had an infinite number of solutions, but we only had a leading entry here, right? For this row, right? For the Y column, there's not a leading entry. But down here, we have a leading entry in each column, right? So there's a leading entry corresponding to each of our variables. And so that actually means that we have an infinite number of solutions. I mean, excuse me, have a unique solution. So it's unique because there's a leading entry in each variable's column. All right, that's a little fuzzy because I haven't really explained why that really matters. But one thing you can notice is that we can solve the system. Right, so we can say, oh, 3z equals 0 means z has to equal 0, right? And then we back up, so we get 2y minus 5z equals 4, and z is 0, so 2y equals 4, so y equals 2. And then we back up again, and I can barely get this on. We've got x minus 3y plus 4z equals -4. And so x minus 3 times 2 plus 4 times 0 equals -4. So what does that say? X equals, got a -6 plus 6, so 2, I think. My algebra is correct. So the solution is x equals 2, y equals 2, z equals 0. All right. Okay, so I got 2/16, we're a little over here. But I do think that we have covered most of sections 1.1 and 1.2. So I would say that before Wednesday, I should try to work on homework problems in those sections. And we can go over homework problems on Wednesday, and then we'll start into section 1.3. All right, any questions? So I'll post these notes, and I'll also post the video that I've taken in a little bit. Thank you all for coming and for participating. And I look forward to seeing you in person next week. Bye, everybody.
Thank you.
Thank you. Bye-bye.
Yeah, bye-bye.